Our research objective is to develop a new front-end technique to reduce insertion errors found in group discussion transcriptions. Unlike speech separation techniques that use deep learning, our approach is essentially VAD, so it works robustly. Algorithm is very simple, but very effective. It can still work without training, so it can work in real time. Our proposed multi-channel VAD is designed as a simple extension of the conventional VAD. In our assumed scenario, each participant wears a crosstalk microphone. So please note each audio track is associated with each speaker. In the traditional approach called single-channel VAD, individual audio tracks are used to determine the active speech segment. Our proposed multi-channel VAD integrates the information of all audio tracks in a group to determine the active speech segment. You may notice this technique implicitly assumes that the participants will not speak at the same time. That is almost true as far as I observe students in junior high school classes. And most of the simultaneous speeches are back channels. Therefore, it may not be a big problem if it is ignored. Our main research target is education. In this study, we evaluated the proposed method using real data recorded in the actual middle school. Another possible scenario would be in a business meeting, where each participant brings his or her own smartphone and Bluetooth earpiece microphone to transcribe the discussion. Let's take a look at the problem we see in possible applications. There are several recording tracks here, each associated with a speaker. It often contains speech signals coming from adjacent speakers. It is known that crosstalk microphones have noise-canceling features, but they actually cannot completely eliminate the sound of the neighboring speakers. Therefore, automatic speech recognition may output a lot of unwanted text unless VAD is used. Of course, in educational applications, such a fake text are very harmful to instructors because they are not what the target students actually said. Simple solutions to this problem would be the use of single-channel VAD, but experiments show its poor performance. The second option would be a use of insertion penalty of ASR decoder, but its tuning is highly dependent on the acoustic environment. The third option is a throat microphone. I know people are not positive to wear it. Also, speech separation technique using deep learning could be possible. However, the deep learning approach may depend on the configuration of the device and the characteristics of the speaker when it is trained. Therefore, we are looking for a pure front-end approach. Distributed microphone array could be a possible solution using front-end technique. However, it requires a period of time where the position of the microphone and the speakers do not move. In our application, a speaker wearing a crosstalk microphone frequently changes the direction of his face. Therefore, this technique is not applicable. We have two core ideas in our proposed multi-channel VAD. Basically, it is a power-based judgment on a frame-by-frame basis. The idea one is all-win condition. For example, let's say we are looking at speaker 1 to determine if it is active or inactive. Then we have 4 pairs like 1 and 2. The power observations of 2 audio tracks can be plotted in 2 dimensions. If the current observation is below the decision boundary, it is positive support that speaker 1 is active. When track 1 wins in all pairs, we can finally determine the speaker 1 is active. Now let's take a closer look at the observations for track 1 and track 2. Most of the observations attributed to speaker 1 are below the decision boundary. Similarly, speech plots of speaker 2 would be above the decision boundary. Observations attributed to speakers 3, 4, and 5 do not contribute to track 1 and track 2, so they are expected to be on the diagonal. Please note, judgments using the decision boundary are made only the area between threshold A and threshold B in track 1, which is regarded as intermediate state. If the observation of track 1 is larger than threshold B, we can unconditionally determine speaker 1 is active. Also, if the observation of track 1 is smaller than threshold A, it should be determined as inactive. The gain setting of the amplifier and the distance between the microphone and the mouth may vary from speaker to speaker. That difference can be a problem for the two-dimensional judgment. Another core idea in this paper is to normalize the gain of the microphone with the power of the ambient noise. Since the ambient noise is common to all microphones, we can compensate for gain differences by dividing by the mean ambient noise power. This paper refers to the normalized logarithmic power as local SNR, as shown in the two-dimensional plots. Next question would be how to determine the decision boundary. The simplest method is just to draw a diagonal line. This is a good approximation and it actually works. However, it cannot handle a poor speaker with a microphone attached at a distance or speaking very softly. Using machine learning, the decision boundary can be estimated on a model of Gaussian or SVM. This paper used a simple method using a centroid as shown in this picture. Please note, decision boundary estimation requires iteration. Next slide explains our iterative process. In the iterative process, the decision boundary is updated by the two centroids. Each centroid represents the distribution of speech plots attributed to each speaker. Attributes of these speech plots are updated by the updated decision boundary. To start the iterative loop, the initial speech attributes are given by single-channel VAD. You may notice part of the initial speech plots are attributed to both speakers. We accepted it for the starting point. We evaluated the proposed method using real data recorded in the actual middle school. The recorded data was manually transcribed and tagged with time information. This table shows the error rate of the VAD. This is a frame-based evaluation. SVAD represents a single-channel VAD. MVAD represents a multi-channel VAD. The diag option implies the use of a diagonally aligned decision boundary, where no training is required. The other two options use training to estimate a decision boundary. However, the no iteration option does not use the iteration for training, while the iteration option uses the iteration. It turns out that even without training, the multi-channel VAD works well and is superior to the single-channel VAD. This table summarizes the results of the automatic speech recognition with or without VADs. None case does not use any segmentation for the transcription. Oracle case uses the manual segmentation. So this is considered as the upper limit of this test set. As a result, we found that the multi-channel VAD works very well, and its performance is almost equal to the upper limit, even without training. Our proposed multi-channel VAD is a practical solution that has been proven on real data. The performance of ASR using this technique can be improved up to the Oracle segmentation level. It works without training, so it works in real time. It is robust to changes in the position of talkers and microphones. It is not dependent on the number of microphones, their placement, or any other configuration of the device. It is also not language dependent.